Yes. Well, first of all, I'm really very glad being invited to this symposium on structured light. And I very much wanted myself to be there for several reasons. One of them is that I spent some of my childhood in Bangalore, when my father was a long-term visiting professor at Indian Institute of Science and Raman Institute, and I always wanted to come back. And unfortunately, there are some certain issues in between India and UK regarding visas, and this prevented me from coming. With all my heart, I'm currently in Bangalore. So my talk is called The Technology of Super-Oscillations. And this work, which has been done in equal shares between University of Southampton and NTU Singapore. And I think that if there is a message in my talk, it could be that we are seeing the rise and the down of pico-photonics. The science and technology of light sort of seeing and interacting with picometer-scale events and objects. So, but I would like to start with perhaps a more, oops, sorry, for some reason my slides do not switch. Well, no, they do. So I would like to show some perhaps more trivial line which represents resolution of optical and electron beam technologies. And we're all very well familiar with that. We know that optics stop at the diffraction limit, and then further advances are possible through nonlinear and statistical and scanning techniques, near-field scanning techniques. Then there's, for optics, there's a considerable window, and where optics doesn't work, and then electron beams takes over. But electron beam microscopy starts somewhere at a scale of a few tenths of picometers, and there's no man's land behind this barrier, right? So I think that this all is being changed very rapidly and quite recently, and I can give you some idea of our contribution to breaking these barriers. So I would start with something which has nothing to do with super oscillations, nothing to do with optics, in fact. It's a technology which we developed in the last 2 years to detect movements in the nanostructures. And we can now routinely detect movements of a picometer-scale amplitude. And how do we do that is explained here. You send a beam of electrons on an oscillating object, such as cantilever. You detect secondary electron beams, and the modulation of secondary electron beams will be proportional to the gradient of edge of the structure, and also will depend on the diameter of the electron beam. If you do your evaluation right, you will get that you can get approximately 1 picometer in 1 second using conventional scanning electron beam currents. So, and this works like that. So if you have an object which moves, a fly here, so when you do a conventional scanning electron microscopy, you simply detect in every point average value of the secondary electron current, right? What we do, we fix our electron beam in a particular edge of the structure and then do the Fourier analysis of that signal. As a result of that, we can build a hyperspectral image of this moving object at a particular frequency of our choice, right? And I give you examples how this can be applied to nanotechnology. So for instance, this is a little cantilever made out of a membrane. We focus our beam somewhere here and then scan it across and doing this Fourier analysis. And you will see that this is image of this structure in terms of amplitude of its oscillation at frequency 117 kilohertz. And this is the frequency in which this cantilever is resonant. So this is nothing but Brownian motion of the cantilever. Brownian motion of such a cantilever at room temperature is about 100 picometers in amplitude at the resonance, at the natural frequency of movement. And you can see that we very clearly see this resonance with different mode of oscillations. And the scale here, the noise level, is at about 1 picometer per second of detection. And the amplitude is about 100 picometers. What is 100 picometers? 100 picometers is 2 times smaller than van der Waals radius of silicon it is made from. So this is clearly an image of Brownian motion in terms of the subatomic resolution. Well, you can do marvelous things with such resolution. There's endless opportunities. What we did recently, we looked at the motion of such cantilever and detected its ballistic regime of movement. What ballistic regime is that if you observe a thermally moving cantilever, its movements will be random. But at short observation distances, it moves in a ballistic regime. You may think that it's about a Brownian particles, which moves between hits of individual molecules. This is a bit more complex here. It's related to movements resulted from momentum transfer from annihilation and creation of flexural phonons. But the message is here. If you can measure very small scale events, small displacements, small amplitudes of oscillations, you have access to a very, very interesting physics. So this is essentially a schedule of my talk. And what I will tell you today, and you perhaps knew about many of these things, but I will show you the latest results as well. And the first thing is that I will show you that the light can be focused in a spot size of any shape and any size. So, complex fields have some very, very small features, which can be imaged by conventional lenses. These small features created by lenses can be used for imaging and microscopy. And this has also impact of nanometrology and sub-nanometrology because of presence of these small features of in super-oscillatory fields. And this can be even used for imaging and a new type of imaging, which is based on illuminating of very small objects with topological structured light. And this is what we call deeply sub-wavelength topological microscopy. And I give examples of all of them. For some reason, the slides do not change. My slides do not change. Can you see change of my slides? Can you not? No, my slide stopped changing. I will stop sharing and switch again.
Now it's showing you only, not your slide.
Yeah. But my slides do not change, so I need to do something about that.
And now your slides are showing, yes.
Yeah, great, thank you. So the first thing I wanted to show you is something very well known now. It's called a super-oscillation, and this is an example of super-oscillation in a one-dimensional function. So say we have a few harmonics, 5 harmonics in this case. We adjust amplitudes of the harmonics and have beating of the harmonics as presented by this white line. If you would be doing this in a clever way, you can obtain a situation where in the central part of this function, there will be a section that doesn't, again, it stops switching. I cannot do anything. My slides do not change. Can you see slide changing or not?
You can see your slides changing?
No, my slides do not change.
Oh.
Okay, I try again.
Zoom installation is all right, or?
No, I can see the room. I can see myself. Maybe I stop my video.
Maybe you rejoin the Zoom link.
So you want me to restart the Zoom link?
Yeah, you may stop it and then restart the Zoom link, please.
Okay. Can you hear me now? Can you hear me now?
Yes, sir, we can hear you.
Yeah, okay. I start the presentation again. Right, okay, it works. So can I continue now? Is it okay? I continue then. So you can arrange amplitudes of this series in a way that in the middle there will be a small feature which only can be seen with great magnification. But this feature is a very short one, and certainly much shorter than the highest Fourier component in the spectrum, right? And this is called super-oscillations. There are many interesting features around super-oscillation. Typically, you would see a very fast phase variation near the super-oscillation, and you will notice very soon that intensity of super-oscillations become polynomially smaller with decrease of the size of the hotspot. So this all started with fundamental work on quantum mechanics by Aharonov, and then it was brought into optical domain by Michael Berry and Popescu. And in optics, a significance of that is that you can focus in a hotspot which is arbitrarily small, but the energy which will go into this hotspot will be reduced polynomially with the size of the hotspot. So we, in 2007, were very lucky to make the first explicit observation of super-oscillation using light diffracted on quasi-crystal arrays of holes. So in the far field, this created a set of spots. And
just
some
a small
of this
suggestion, Nikolay, just a small suggestion. You may switch off your video. That may improve this connection, okay?
Yeah, okay, I will switch off my video.
Yeah.
Right, how do I do that? I don't know how to do that.
It's okay, no problem. You carry on, please.
Yeah, but I'm trying. Okay, so if you see it aggravated, so let me know. I will find a way of switching the video. Oh, stop video. Okay, right. So we did it by observing the far field using a tapered optical probe. But in fact, you do not need to do that. You simply can see super-oscillatory hotspots by a conventional lens. And the reason for that super-oscillatory hotspots are formed by free space waves, and therefore can be imaged by a conventional lens. And this is extremely important for all applications of super-oscillations. So the hotspots can be transformed, magnified, and conveyed by conventional optical devices. So in 2009, we published a paper which I think is very important was very important for us. We established essentially a protocol on how to create a mask with certain transmission and phase characteristics, which will create a super-oscillatory hotspot in a certain range of distances with arbitrary hotspot. So you say, I want a hotspot which is following shape, following diameter, give me the mask. And this paper, 2009, in Nature Nanoletters was establishing such a procedure mathematically. So as a result of that, we started working on various types of super-oscillatory lenses. And I give you a few examples of that. Well, I started with quasi-crystal arrays of holes. It's not a very good lens because it creates messy distribution of hotspots. So the best possible could be achieved if you can control the density and the phase retardation of a screen. And this would create you opportunity to make a hotspot of any size. We explored various versions of super-oscillatory hotspot, in particular very elongated ones, which might be of interest to data recording, for instance. We manufactured and created super-oscillatory lenses, mostly two-dimensional cylindrical symmetry lenses with using various types of binary masks, in particular in metal films and in dielectric films like silicon, for instance. I would like to tell a bit more about two types of lens before going further. So these are sort of engineering examples of how these lenses were created. Here on the right, perhaps, is the most impressive lens, which is created on a commercial silicon wafer and cut into ready device for application. So one of the interesting possibilities is to create achromatic and apochromatic super-oscillatory lenses. How it's done is that you create a cylindrical binary structure, for instance, binary transmission structure, and it makes a few hotspot along its axial direction. And you design it in a way, and when we developed protocols for designing that, at certain distance from the lens, different frequencies, different wavelengths, different colors coincide in one particular point. And I give you example of here at this corner, you can see example of a white light super-oscillatory lens, which combines the blue, the green, and the red colors all together. Perhaps technically most advanced, what we call metamaterial superlens 2.0. We all know about metamaterial superlens made out of negative index material. It's a great idea. So unfortunately, it didn't materialize it as a practical device in the optical part of the spectrum. And there are several reasons for that, mostly technical. But we are not talking here about a negative index material. We are talking about super-oscillatory lens, which is designed in the following way. You start with your desired hotspot, which typically has a central hotspot and then a halo of high intensity, which is inevitable. So, but you are engineering the hotspot here. You then propagate this using band-limited functions, and a good way to do that is using prolate spheroidal functions. You then understand what mask must be at a certain distance. It should be amplitude mask and should be a phase mask simultaneously. And what you do, you divide your mask plane into several enclosed circle areas and fill them up with metamolecules. And metamolecules are these plasmonic little creatures which are designed to provide necessary phase and the necessary amplitude as predicted by backpropagation. And we manufactured such lenses, I think very successfully. Typically, this lens would have several thousand, 9,000 metamolecules, properly arranged. All of them are different to get correct phase and intensity correction to the wavefront. And these are examples of such lenses. You can see here that we have numerical aperture nominally exceeding 1, which is impossible with conventional lenses. And that means that we can focus on a very small hot spot and a pretty large area around the lens, which is have low intensity background. And you can see here a typical trait. So if you would like to have backgrounds higher, bigger and bigger and bigger, so this free area, dark area around the central hotspot, you are losing proportionally the intensity, the proportion of light intensity going into the hotspot. But these lenses have been manufactured in various versions and used in our device applications. And we created essentially a new type of super resolution microscopy based on super-oscillatory hotspots. And of course, this is initially, from 2008, was initially simply extension of the work with quasi-crystal arrays. What we have demonstrated, and this is sort of a trivial result, but it was demonstrated experimentally, that if you have a point-like source, which is tapered fiber, and you eliminate quasi-crystal arrays of holes, you have a focus. And if you move this across, the focus moves. So this is the main function of a lens, in this case with magnification 1. But when we developed a much more sophisticated lenses, we created a new imaging technology, which was based on illuminating your subject, your object here, with a super-oscillatory hotspot, right? And then picking up light from this hotspot using conventional lens in a confocal arrangement. And this can clearly show you that if you apply this super-oscillatory confocal method to imaging, the smaller your hotspot, and you can engineer any size of the hotspot here from 0.56 to 0.33, you see that hotspot become smaller and resolution improves. And this beats several times over a conventional numerical aperture lens with conventional lens with a similar numerical aperture. So this works like that. Again, sort of, I just quite like the comparison with the STED, stimulated emission depletion methodology, which was developed by Stephen Hell and got Nobel Prize for very good reasons. So what they did, they impregnated the object of study with a luminescent material and then start scanning it in such a way that only in the central hotspot the luminescence is not bleached. Otherwise, around this little hotspot in the center, the luminescence is bleached by high intensity light, right? And this is an essence of STED methodology. What we do is exactly the same, but positive. First of all, we do not need to impregnate our object with luminescent material. There's nothing to bleach here. Our technique is truly linear. We simply create a small hotspot and scan with that using confocal arrangements. So I would like perhaps to don't spend much time on that, but there's interesting physics behind that. We achieve super resolution in a linear system, which is band limited. And this is possible because in this technique, image obtained with a band limited function is actually super oscillatory. And this creates a much higher level of resolution than in conventional confocal technique. And again, the resolution will go with the size of the central hotspot. So this is video. I'm not sure if you can see or cannot see the video, but this shows a biological application of this technique to detect actually stem cells and in particular propagation of philopodia in this stem cell. In these oval areas, you can see appearance of spikes, and these spikes right now. And the spikes is a propagation of the cell to explore environment around it. And this we now have a microscope in biology department here in Southampton, which operates with about 30 frames per second, and does very, very interesting work. So from now, I would like to go to the next level, and this next level is based on the idea of topological structure of super-oscillatory field. So far, we explored only intensity of light. So we explored the fact that you can have a hotspot smaller than the wavelength of light. You cannot go much further than typically lambda by 6, lambda by 5, because when the hotspot becoming very small, signal to noise ratio decreases because intensity going into the hotspot is reduced polynomially, as I said. So what we would like to do is to exploit other features of a super-oscillatory light field. And to explain that, I give you an example of a sketch of a presentation of what happens in a hotspot of a conventional lens. So this is intensity hotspot, light going from left to right, and you see a Gaussian beam focusing. So this the white arrows are pointing vectors, obviously. When you have super-oscillatory hotspot, what happens is that on both sides of the hotspot, you would see creation of backpropagating electromagnetic energy. So this area, there will be here a whirlpool of optical radiation. Optical radiation will go like that. As a result of that, this nano-vortices will squeeze the hotspot and make it smaller. And this is, in essence, what makes super-oscillation hotspots. So the upper one you can basically generate with a Fresnel wave plate, and here you need much more complex super-oscillatory zone wave plate, which do this by very precise tailored interference of multiple beams. So we, in 2019, after quite considerable effort, we have been able to map, really map in experiment many topological features of super-oscillatory field. And the way we did that, I will explain in a second because it's important. We started with creating a super-oscillatory meta-surface, which is exploiting the geometrical phase effect. So this meta-surface has slits, rows of slits, and I deliberately colored them slits with different directions, which are directed at 45 and minus 45 to the vertical. This would be a structure which will create one-dimensional super-oscillatory field. And we use the fact that light transmitted through slits with different orientation would have geometrical phase retardation corresponding to pi. And as a result of that, you can eliminate such a structure with a plane wave. And depending on the polarization state of light, if it is the same as the incident plane wave, it will not be at all affected by the metamaterial. But perpendicular polarization component will see this structure become diffracting on this structure. And if you do the structure correctly, you can create super-oscillatory hotspot. And this gives an incredible opportunity to do interferometry of this hotspot. What you simply do, you simply look at the structure with a conventional lens and detect intensity when you scan the lens across the field distribution. You need to apply a polarizer to mix two polarizations, the vertical and the horizontal. And in fact, technically, to do the full interferometry, the full intensity and phase mapping, you need to do 4 experiments with 4 different input polarizations, which is horizontal, vertical, circular left, circular right. But this is well described. But as a result, you get information about the exact phase and intensity pattern of this field. So important thing is this is a very small device. We are talking about a metamaterial which is 50 by 50 micron in size and very small areas propagating sort of a few tenths of micrometers from the surface. It's an extremely robust interferometer in a way. And it does marvelous things. So it allows you to map the intensity of the hotspot. Light is coming from left to right. It allows you to map the phase portrait of the hotspot. And you can see this is the super-oscillatory hotspot. This vortices around this will be phase singularities here. And you can map your phase and in particular discover that around certain points there's a giant gradient of the phase which Michael Berry calls local wave vector, and indeed is a local wave vector. It may be considerably tens of times higher than the wave vector of free space. And very interestingly, pinned to the singularities here, you can see areas, these white areas, which are energy backflow zones. And all of them are present in super-oscillatory light field. The good news is that also the hotspot is not that small. It's only a fraction of diffraction limit. The zones of energy backflow and areas where K vector is high are very, very small. They're a small fraction of the wavelengths, typically lambda by 100, but it depends, of course, on the type of mask you use for that. This brings me to a very, I believe, important observation on sort of unsolicited similarities between plasmonic fields close to the surface of a metal and super-oscillatory fields in free space. First of all, they have a lot of similarities. First of all, in evanescent fields of plasmonics, high K vectors are present, right? There are phase singularities. There are zones of energy backflow nano-vortices. And this can be seen on this example of light passing by a resonant plasmonic nanoparticles. So you see that the Poynting vector is circling around the structure here. And this is, of course, very, very similar to this nanovortex in the super-oscillatory field. More to that, as I said, efficiency of focusing into the hotspot in super-oscillatory field is a polynomial reduction of its size. Exactly the same happens with intensity of light transmitted through a plasmonic plasmonic hole. So typically, light transmitted to a hole to two corrections is a fourth order of ratio between diameter and the wavelength. Exactly the same scaling. But the difference is that in plasmonics here on the right, you observe these features in the evanescent fields in the presence of dissipation. Here, it's free space field and no dissipation. Okay. Okay. My picture doesn't switch again.
Changing?
Yeah, I have to restart again if you don't mind. There's no way around that. Can you hear me? If you can hear me, I can continue then. Can you hear me?
Yeah, yes, sir, we can hear
Okay,
you.
See your slides.
Well, I will try to run faster, but inevitably. What I wanted to now to do is to discuss how these topologically structured elements of the field can be used
we
in
don't see your
metrology.
slides yet. You have to share your slides.
Right. Okay. Can you see it now?
Yes, we can see your screen, but not your slides yet. Yes.
Can you see it now?
Yeah.
Okay, very good. Right. So what I wanted to continue with is how to use this topologically structured fields in metrology and imaging. So the idea of metrology is very simple. So if you have features of light which you can image, and these features are very small, you can use this as a ruler in metrology. So if you look into the beam of light as it comes to you after focusing the super-oscillatory field, what you will see intensity map, which has relatively large features, and the wave vector map, which we just detected using this interferometry, which have much more tiny zones of high value of K vector. And this can be used as optical ruler. So if in a conventional ruler, your resolution is limited to diffraction of light by lambda by 2, right? So here, you're in optical ruler, if you create very narrow localization of something you can detect, in this case, zones of high K vector, you can use it for metrology. And we did exactly that. So we created two platforms. One platform had a laser and this geometrical phase metasurface. On the other platform was a microscopic lens and the polarizer. And as a result of that, we can scan this field structure, detect positions of the high areas of high K vector, and make a displacement metrology. And it immediately gives you a very simple technique with resolution of about under 1 nanometer. So, the idea now which we pursue is how to use these features in microscopy and metrology of really small objects, of nanoscale objects. And the idea is sound crazy because how can you get in imaging and metrology sort of deeply beyond the sub-wavelengths, deeply beyond the sub-wavelengths? And the reason for that is, of course, that in optical part of the spectrum, the wavelength is a few hundred of nanometers. And what we want to achieve is measuring something with sub-nanometer resolution. And therefore, we have a disconnect of several thousands, right? So how the light-matter interaction may be sensitive to such a small features. And this is, of course, a very correct logical sequence, but we are not going to use plane waves. We are going to use a highly structured topological light in the form of super-oscillations and use its topological features to do the imaging. So I would like to have a reference back to a famous paper by Michael Berry, 2010, when he actually spotted a very important thing is that a combination of a few coherent plane waves, in this example, is about 50 coherent plane waves. If they sort of semi-randomly directed, you will create a field which has a lot of singularities, a lot of zones of high K vector values, and a lot of zones with energy backflow. This is native, this is natural to complex topologically structured light. So our idea for imaging is we have an object, and this is just artistic impression of a small object. We put it in topologically structured field, and then we move it across the field. And we move it across the field. Every time it moves, we measure scattered field. And of course, this brings up to the inverse scattering problem, which is, as you all perhaps well aware, is very difficult and ill-posed. And this is where we will engage artificial intelligence in the form of deep learning. So we will analyze the scattering field from certain test objects, train the neural network to recognize these variations, and then we'll be trying to make sense out of scattering patterns of unknown objects. We rely on a very important fact, which I need to flag here. This is the intensity and the phase of a super-oscillatory spot. This green spot is a small particle, really small particle, lambda by 1,000. And what we do, on the next slides, we plot change of scattering pattern, which resulted from displacement of the particle and positioning a very small scatter in the field. And you will see that these maps, which represent detector position and particle position, are very, very highly structured. I don't think I have time to explain everything, but trust me on that a very strong variation of scattering pattern may be seen when the particle passes by a singularity. And this is perhaps better illustrated here. So if you have small particle, you have incident light, and then you move your particle against the light field. If only intensity variation happens, you will see in certain direction intensity change. But if intensity and phase variation change, so the particle goes across, say, a singularity, there's additional change which is related to the phase change. And in certain circumstances, it may be very, very big. And this helps to create a situation where small elements of structure interacting with vicinity of the nanoparticle, vicinity of the singularity, will create a small change of diffraction pattern, which we are going to use. So, so the idea is very simple. You illuminate with topologically structured light. You put there an object, and train the system by showing different objects, different insects, and then the network learns the features, and then you put your known object and network recognize object. This is, of course, seriously simplified picture, but this shows the method. We started with something more simple. We started with doing this with a plane wave illumination, just to understand how artificial intelligence can help. So what we did, in a nutshell, we created a large array of very, very tiny slits in a metal film. We show this to illuminate this plane wave, image the diffraction pattern of each of the slits, and this is an example of how the diffraction pattern look like. We use information about the slits dimensions and position and the interference pattern to train the neural network. And then when you show neural network a slit, it will tell you, neural network a diffraction pattern, it will tell you what the slit width was. It works even with plane wave illumination remarkably well. Again, in interest of time, I will simply say that in a conventional microscope, in a trained system, training achieved in only a few hundreds of slits, you can achieve resolution of optical measurements, which is exceeding lambda by 200, by nearly 300, 260. So at a tune of a few nanometers when visible light is used. And this actually already challenges resolution of scanning electron microscope, which is at our disposal, conventional scanning electron microscope, and Fox-Stein beam system, which used to manufacture such slits in a metal film. So this is a remarkable thing. And this is beats optical resolution limit for several reasons, which I explain maybe at the end. I started with showing you this picture when a beam of electrons is scattered and we detect small movements of a cantilever, small oscillation of the cantilever. Our aim is to do this exactly the same with optics, but instead of electron beam, now using topologically structured light, which is focused in the vicinity of the edge of the structure. And instead of using detection of secondary electron, we use scattered photons. This is the whole idea. We so far have been able to progress it in the following way. So this is a nanowire, which is manufactured in a nanoscale membrane. And this nanowire is made of silicon, 50 nanometers of silicon covered with gold, and is placed between two sides of the membrane. And you can, by applying electrostatic voltage between the nanowire and the rest of the sample, you can move this nanowire. You can move it very, very efficiently with great accuracy. And so this is sort of an ideal object for artificial intelligence assisted microscopy, because if you are interested in position of such an object, you can train the system on itself, right? And this is what we did exactly. So we did this with plane wave illumination and super-oscillatory illuminations. This is a very demanding experiment because it needs to be done in a very short period of time to eliminate various mechanical movements, and it requires a very accurate and sophisticated measuring of the position of the nanowire to achieve the ground truth. But at the end of the story, it looks like that. So this is error in optical measurements of the displacement using these techniques. When you train the system by applying known electric voltage between the nanowire and the rest of the membrane, and therefore control displacement. And then you show the nanowire of unknown displacement to the system. So we exercise the displacement from 10 to 1,000 picometers. So from 1 nanometer below. And if you use optical plane wave illumination, the resolution is to a tune of about 100 picometers. It increases when you use super-oscillatory illumination, roughly a factor of 2 or 3. And we are working now on improving and better understanding that. But as a matter of fact, we now operate with a technique, all optical technique, which can measure displacement over cantilever with certainly subatomic
Sorry,
radius.
Nikolay, you have to wind up now because.
This is the last slide. This was the last slide, right? So, so I will show you this last slide, and this is the whole point of the presentation, is that with optics, we can now go to the level of comparable with the Brownian motion. And because the single shot measurements technique, you can now, by using high-speed cameras, combine it with really high-speed frame rate measurements. And this is exactly what we are doing right now in Southampton and in Singapore. And I wanted to conclude my talk with that. Maybe I will skip this for discussion. This shall be in the presentation recorded. This is a timeline for various discoveries in super-oscillation. I also skipped that. But what I wanted to say is that this ability to, with light, to see sub-nanometer scale events, picometer-scale events, is open in our view, the case for pico-photonics, not nano-photonics, but pico-photonics, the science of interaction of picometer-scale objects and events with light. And I list here a non-exhaustive list of topics which might be addressed by using this technique in fundamental and applied science research. So I wanted to finish with that. I only wanted to give credit to key people who were involved in this work in recent years. And if you want to see more, you simply can download my review, which we wrote with Guanhu Yuan in Nature Review Physics, and this is the address. So thank you very much for your attention.
So maybe there is time for one quick question.
Yeah, I have a question which has two parts. One is, can the speckle patterns be seen as super oscillation field? And the second part to it is the caustic pattern that you get typically in a scattering light field. Can they be considered as a structured field for and can be used for imaging purposes?
Thank you for your question. So I need to say that I understood only the first part, and I will reply on that, and then we will see how it works. So yes, speckle patterns are typically super-oscillatory fields, and there's a paper which was written a few years ago by a former student of Michael Berry, which his name is Mark Dennis. And Mark Dennis examined complex pattern, statistics of pattern created by multiple light beams. And he concluded that essentially 30% of all patterns created by 30% of area of all patterns created by current light beams, in particular speckles, are super-oscillatory. Sorry, can you repeat the second question? Can you please repeat the second question?
The second part is the caustics pattern that you get. Can it be used for imaging purpose that you are mentioning about structured light being used for imaging? Caustics. That again, Michael Berry has talked about it long back.
Yes. They can.
Can they be considered as structured light and be used for imaging purpose?
Yes, the answer is yes, but not in a direct way. But again, the only way of going ahead with any complex structural elimination is using deep learning process. And there is now a paper published by a group of mathematicians in Japan, which explains why a neural network approach can actually solve very, very accurately the Fredholm integral equations, which is essentially the equation behind the inverse scattering problem. And additional information which comes to this process is the information which is accumulated during the training process. And this excessive amount of information acquired during the deep learning process is the source of high resolution. Yes, but any sort of complex field can do very well in this sort of imaging, in my view.
Maybe a very quick question and make your
Thank you,
question
sir,
very
for
precise.
your nice talk. So I have a question, like you told that the evanescent wave, especially the nano-vortice, is squeezing the spot size for the super-oscillatory hotspot. So how small that the hotspot can we make? Means what is the dependence?
Maybe I was not. Can somebody let my video be visible? Because I'm stopped from showing my video. Can you help with that? I cannot show my video, which is which.